Alright, so as a form of review from last class, what you'll see is that you guys will see that there are slides that are complete on my end, but incomplete on your end. So what's going to happen is that I will post basically the answers to those slides after, but I didn't want to give you the answers now because a little bit of an in-class exercise to see your level of understanding based on the stuff that we did in the last two lectures. So, as a review, we talked about oxidative phosphorylation, basically the relationship between substrates and products, and we said that if we change the concentration or the amount of any one substrate, we can modify the rate of flux through this oxidative phosphorylation pathway. If we change the number of enzymes or the activity of enzymes, we can increase the rate of product production at a given level of substrate concentration, and so on and so forth. We talked about basically how these substrates in the presence of mitochondrial enzymes can generate ATP through oxidative phosphorylation and generate force in order to support a given ATP demand or a given external power output, for example. And we also talked about how important it is for muscular function to try to keep the cellular milieu, so the metabolic milieu, within check. And particularly trying to limit the extent to which hydrogen ions increase within the cell. So try to limit pH or intracellular acidosis, because it does have effects on muscle contractile function. And in particular, try to limit the extent to which we have increases in intracellular inorganic phosphate levels. Because it, in particular, has very dramatic effects on cross-bridging sarcoplasmic release of calcium and various other things. And so it itself is a molecular determinant of muscular fatigue, ultimately a performance limit. So we would like to try to limit the extent to which these metabolic byproducts accumulate in the cell. So, a question, and this could be a question that occurs on a midterm or on a final, which is to say it is a question that you will see, is if one effect of exercise training, so again, you go from sedentary to trained over 8 weeks, 12 weeks, whatever it is. If one effect of exercise training is to increase the number of mitochondria and the number of mitochondrial enzymes, the question I'm asking is, what would we see if you had to draw a plot in terms of intracellular ATP, phosphocreatine, ADP, PI, lactate, and hydrogen ion concentrations in the quadricep muscle fibers at the end of 15 minutes of exercise at a constant VO2 of 2 liters a minute after 6 weeks of endurance training. So what you have now is you've got 15 minutes of exercise, steady state exercise. This is the pre-training. I wish this thing would be better situated. And then we got post-training, okay? So these are the baseline values. So basically pre-training, you can see this little line. These are basically the post-training values. The question is, what happens to VO2, ATP, phosphocreatine from the pre to post condition? Does it increase? Does it decrease to a new steady state level at a given VO2 of 2 liters a minute? So we'll step through each of these parameters individually. So the question is, first, from pre to post training, the VO2 is 2 liters a minute. Okay, so it's a fixed VO2 requirement. So would we see that VO2 in the post-training condition would be higher, lower, or the same as it was in the pre-training condition? Be the same. So the same VO2 or metabolic requirement. So in this case, VO2 would be the same. Now we said that there was a relationship between ATP demands, external power output demands, and VO2, such that those relationships were linear. Remember that 4-plot diagram? Started from the top left, moved to the top right, down to the bottom right, over to the bottom left. So we kind of went through that but the deductive reasoning of how we can look at VO2 as an indication of aerobic ATP supply. So if VO2 is fixed, pre and post training, do you think that the ATP requirements are higher, lower, or the same? They're the same, right? So same VO2, same power output is going to require a similar ATP demand. So in this case, the intracellular ATP concentrations would be similar. And again, we have to match ATP supply and demand. Remember, ATP is a regulated variable, so we have metabolic pathways, the 3 metabolic pathways that we're working to buffer and try to maintain ATP concentrations for a given work rate or given metabolic demand. So the ATP is protected, but the contributions of the different metabolic pathways may vary depending on the training status, the number of enzymes, the activities of the enzymes, the amount of oxygen, whatever it is. Okay? So, VO2 demands and ATP demands are fixed, pre to post training. So now you've gone from basically being sedentary to doing 6 weeks of endurance training. So now you're running 10 kilometers a day, 3 times a week for 6 weeks. So what happens to the number of, so you have an increase in number of mitochondria and number of mitochondrial enzymes. So to support this given VO2 and to support this given ATP demand, will you have more or less phosphocreatine degradation? Less. You need to rely, So your phosphocreatine levels in the muscle will be higher because you're utilizing phosphocreatine less to rephosphorylate ADP into ATP. Right? So to support a given ATP demand, if you have more mitochondria and more enzymes, you can drive oxidative phosphorylation at a higher rate, therefore produce more ATP aerobically, and therefore you need to rely less on phosphocreatine degradation. So the phosphocreatine levels in the muscle after training relative to before training would be higher because you need to use that potential energy source less. What would then happen to the amount of accumulation of inorganic phosphate? What would happen to inorganic phosphate as a negative byproduct that occurs as a result of glycolysis and phosphocreatine degradation and stored ATP breakdown? Right. So inorganic phosphate levels would be lower. What? Yeah.
So you don't use your phosphocreatine system as much, but then why would you do more? Because you're using more oxidative phosphorylation, correct? So it's treated. Why is the phosphocreatine level really useful at a higher level?
Because you don't necessarily need to break down the phosphocreatine levels. Yeah. Okay, so now inorganic phosphate would be at a lower concentration post-training than pre-training, which again is a good thing in terms of fatigue development, because now we should have a metabolic state of the muscle that allows for cross-bridging and sarcoplasmic release of calcium and various other things to occur more effectively. So again, along that plot, if you remember that plot, this is 50%. We have a situation where pre-training, post-training, it'll take you longer in terms of time to reach the performance limit if you accumulate inorganic phosphate at a slower rate. What would the ADP levels look like? Again, think of it this way. ADP is a stimulant to glycolysis, so the rate of glycolytic flux is lower, we have lesser of a stimulant, so the ADP levels would be lower. What would happen to intramuscular lactate or even blood lactate levels? Would they be higher, lower, or no different? Sorry? Lower. And for every lactic acid ion that's produced, it dissociates into a hydrogen ion and a lactate ion. So presumably if there's less circulating lactate or intramuscular lactate, there should be less hydrogen ion. So this is an example of kind of to put it into context. Okay, I go from a state where I have an untrained muscle to a trained muscle. And these adaptations would allow with more mitochondria and more mitochondrial enzymes in order to support a given VO2 and a given ATP demand, less reliance on the ATP PCR system, less accumulation of fatigue-causing metabolites, lesser reliance on glycolytic flux to support a given VO2, to support a given relative task. Again, I harp on that because it doesn't matter, this is a hard thing to interpret if you're exercising at 2 liters a minute of VO2 pre and 3 liters a minute post. You haven't standardized the stimulus. So when we're evaluating this, it's at the same VO2, it's at the same ATP demand, it's at the same external power output. This becomes very important in clinical physiology. Because if I want to know, you come in with a good heart, I do an exercise test and I exercise you at 75 watts, and then heaven forbid you have a heart attack, or you get coronary artery disease, or you develop emphysema. If I do a follow-up test at 50 watts or 100 watts on the bicycle, I have no idea if you're improving or not because you're performing exercise at different intensities. So do I know you got better or worse because of the disease or because of the difference in the stimulus to exercise? So you need to standardize the stress in order to know whether or not somebody's getting better in response to therapy, getting worse in response to age or disease, improving as a result of rehabilitation, deteriorating as a consequence of therapies. So you need to standardize the stimulus. So that's often the way that we'll look at physiology in this class and exercise pathway, is some form of standardized stimulus. So we talked about the oxygen uptake kinetics, right? The O2 deficit. So we said that the VO2 uptake kinetics are basically a mirroring reflection of the ATP, the oxidative phosphorylation kinetics, the turning on, right? The faster VO2, the smaller the oxygen deficit, the faster oxygen uptake basically reaches a steady state, which means the faster oxidative phosphorylation turns on. So as the oxygen deficit gets smaller, oxidative phosphorylation is able to activate more quickly, which is a good thing, right? So what differences would you expect to see in terms of time course of oxygen uptake kinetics? So in other words, I'm asking you, would the oxygen deficit be higher or lower? Would you have more area under the curve or less area under the curve in the rest to exercise transition following 8 weeks of bed rest? This is like space flight, right? You go from here into the atmosphere, you lose the load-bearing aspect of muscular activity. It's basically like laying supine and not doing any physical activity when you're in space. It just strips the muscle away. You try to do countermeasures in space to make sure that you maintain muscle, so they put you on harnesses and get you walking on a treadmill to try to actually load the muscle. Otherwise, the weightlessness just the muscle just begins to strip away, and they come back down to earth, and sometimes they can't get off the shuttle and walk because their muscles are so deteriorated. So, point is like if you have bed rest like that, periods of prolonged physical inactivity, what would happen to the oxygen deficit? Would the oxygen deficit be higher or lower? In other words, would it take oxygen uptake kinetics longer to reach a steady state and oxidative phosphorylation longer to turn on, or slower to turn on? Longer and slower are the same. I need another coffee. So, we've got the oxygen uptake kinetics, which again are a reflection of the oxidative phosphorylation kinetics. Okay, and we've got the pre-bed rest here in the light blue and the turquoise, and the post-bed rest in the darker blue. And so you can see that going from rest to the immediate exercise transition, in the pre-bed rest, so this would be like in the fitter state, better cardiorespiratory fitness, you see that you got a faster acceleration to achieve the steady state value than you do in the post-bed rest condition. So in this case, the oxygen deficit would be the area between the demanded VO2 and the measured VO2, so that area under that curve would be greater. So it's taking longer for oxidative phosphorylation to turn on after a period of 8 weeks of bed rest. So you break your arm, break your back, you break your leg, you get casted, right? Anybody's had a cast, they take a cast off, you got this tiny little calf, you got one big leg, one little leg, you look weird, trying to figure out, you're just sitting there walking around doing this all day. So the idea is, you can see that there's clearly a deterioration at that level of the muscle. So physiologically, what are some of the mechanisms that might explain that change in the oxygen deficit? So what's the opposite of what we just showed? Yeah?
I was
was gonna say decrease maybe mitochondrial enzymes.
Exactly. So there's many aspects here to provide a physiological rationale. The stuff that we haven't talked about in the class, but you know, many of you exercise and are, I'm sure, are aware. So fewer mitochondria, fewer mitochondrial enzymes, have changes in training-induced changes in muscle fiber type composition. So you move from more an aerobic fiber type, so oxidative type fibers. Again, these slides will be posted after lecture. So you move from more like a type 1 predominant muscle fiber to a type 2A and 2X predominant muscle fiber. One's more oxidative, one's more glycolytic. Okay? One's more fatigue resistant, one's more fatigable. And also an impaired oxygen delivery support systems. Less capillaries, blunted heart rate responses, altered cardiac output responses, changes in the microvasculature. And so if you can't supply as much oxygen to the muscle, now you have an appreciation is that if you change intracellular oxygen levels in order to support a given ATP demand, you would have to have a higher or lower rate of glycolytic flux to supply that ATP. That's the question. With glycolysis, so again, he stops pushing as oxygen, the car. What do we have to do is store ATP and phosphocreatine in glycolysis to match that speed. Do a little bit more, right? So if you have impaired oxygen delivery support systems, maybe the intracellular PO2 levels are not as high as they could be. So to support a given ATP demand, you got to increase the rate of glycolytic flux. You got to break down a little more phosphocreatine, you got to rely a little bit more on stored ATP. But that has a consequence in terms of the metabolite accumulation, particularly the accumulation of inorganic phosphate and the rate at which the muscle develops fatigue and the time it takes for you to exercise, or the power output that you can sustain. Okay? All right, go to something slightly different here. We're going to go back. This should be easy peasy now, so we'll try to fly through. So don't be shy, just throw your hands up, give the direction, okay? So what would we see in terms of all of these things again? ATP, now we've got intracellular PO2 in there. Okay, so now we threw in one of the other factors in the substrate ratio there of oxidative phosphorylation, all the other parameters in the quadricep muscle fibers at the end of 15 minutes of exercise. Again, at a VO2 of 2 liters a minute, you'll see I switched this up a little bit, but switch from breathing room air, so normoxic room air, 21% oxygen, basically no carbon dioxide, balance of nitrogen and other inert gases, to a hyperoxic gas mixture. So let's say we go to 50% inspired oxygen, okay? We do this in the clinical physiology lab. People desaturate, we give them 40 or 60% inspired oxygen, increases the driving pressure of oxygen dissolved in the plasma, which can prevent blood desaturation, right? So, and then in part 2, we move to hypoxia. So basically like going from room air or sea level to say altitude. But you can do that by having somebody breathe in a gas from a tank that has, say, 12% oxygen instead of 21. Okay? So, in the hyperoxic state, exercising at 2 liters a minute, does the oxygen uptake requirements, are they any different? It's a standardized task. You're exercising at a fixed task. So VO2 would be the same. If VO2 is the same, are the ATP, overall ATP requirements the same? Yes. So, if we go from breathing 21% oxygen to say 40% oxygen, presumably what would happen to intracellular PO2 levels? Increase. So we have higher intracellular PO2 levels. Now, more oxygen means a greater rate of oxidative phosphorylation, which means that now he's pushing more. So we can take a break as glycolysis and ATP PCR systems. So what are the consequences of that going to be in terms of the phosphocreatine levels? More intracellular PO2 is just like having more mitochondrial enzymes. So what are the phosphocreatine levels going to look like in the muscle if you can measure them through a biopsy? Inorganic phosphate, ADP, lactate levels, hydrogen ion levels. So in hyperoxia, presumably, you should be able to exercise longer. Because you delay the rate of accumulation of fatigue-causing metabolites, because you shift the ATP providing energy supporting system more towards oxidative phosphorylation and away from the anaerobic system. Now, we go from normoxia to breathing hypoxia. We go from sea level to altitude, as an example, a pragmatic example. Has anybody tried to, have you been to Colorado? I mean, you see, MBAs, I don't like basically any other sport other than basketball. But you hear it all the time, is like teams end up in Colorado, they end up in Denver, they're playing at altitude, first quarter they're dead, right? Because there's a hypoxic stimulus there to not only ventilation, but to muscle fatigue, and this is one of those explanations. This is likely what's happening to their muscles. Now, they're not exercising at a steady state, but nevertheless, these are the consequences of being in a hypoxic condition. So, VO2 and ATP, higher, lower, the same. Intracellular PO2, so you're breathing in less oxygen. If the oxygen transport chain goes all the way down to the cell, less oxygen breathed in at the mouth, presumably less oxygen at the level of the cell. There may be adjustments to compensate, but for theoretical purposes, say we have less intracellular PO2. So now we're back into the circumstance where he's not pushing again. So to maintain the same speed of the car, what do the other ATP support systems need to do? They need to increase their activity. Consequences of that are going to be more or less degradation of phosphocreatine, which has what consequence on intracellular PCR levels? They're going to be lower after 15 minutes. Inorganic phosphate levels will be higher or lower compared to the normoxia condition. Higher. ADP levels will be higher or lower. Again, ADP is a stimulus to glycolysis. Lactate levels will be higher or lower. And hydrogen ion levels will be higher or lower. Higher. So, you can kind of systematically begin to look at physiological manipulations in environment, health status, whatever it is, and start to break down. It's like, well, why is somebody not able to exercise particularly well? Well, you have now a theoretical physiological framework to start working through it and understand. It obviously gets more complex because there are multiple change and multiple interactions between the lungs and the heart and the muscles and the nerves and the central nervous system that are trying to protect oxygen delivery and various other factors and compete with all these regulated variables. But if you can manipulate these aspects at the level of the cell, this is, presumably if you could take biopsies or have very sophisticated real-time monitoring of what's happening in the muscle, this is presumably what you would see. And show you some evidence that in fact this is through like phosphorus-bound and magnetic resonance spectroscopy, some pretty cool stuff that actually supports these concepts, but that'll come later on. All right, so moving in a little bit more to kind of what the lab, yeah.
I just had a quick question. You know how some athletes wear their masks to like decrease your oxygen like uptake stuff? Does your body like really adjust to a point where it's like when you take it off, you're like better at it, or does that just like?
I don't know, like, I mean, those hypoxic masks, they're basically, if I understand those correctly, I mean, what they're doing is they're little resistors.
Yeah.
So it's basically an inspiratory threshold load. So instead of breathing like we're breathing now, what they do is they basically put tissue paper. So you breathe through an orifice that has little holes in it. Instead of breathing through a hose, you breathe through a tube. It adds a resistance, which makes the respiratory muscles do more work. Now, there's a whole, so the thing is that I don't believe that it causes hypoxia. I don't think the studies have been done, but they're called altitude trainers. It's BS. You need to cause hypoxia to mimic altitude. So if you just give an inspiratory resistance, but you don't become hypoxic, then it's just a respiratory muscle training. Then you're into a whole other debate. Respiratory muscle training, the respiratory system of all of you in here, unless you like are 20 years old and somehow you developed emphysema or bronchitis, or you have some pediatric disease, you were born prematurely and you have bronchopulmonary dysplasia and some weird, like related growth of your pulmonary vasculature and you're susceptible to ventilation perfusion defects. Training your respiratory muscles really does nothing because your respiratory system is so incredibly overbuilt for your cardiovascular system that if you do get a benefit, it's likely placebo. So the answer to your question is, my bias is that you just have people, I used to live on the canal, in the machine canal, I see guys running around with these masks on, and I couldn't help but laugh. I'm like, they got you thinking that this is gonna work. So it might be a placebo effect, but physiologically, I don't think breathing on these altitude trainers, which are inspiratory resistance trainers, are really all that beneficial. You can strengthen the muscles, but when the muscle is really, really strong to support the demands of exercise, a stronger muscle is no longer beneficial. Right? You can drive a Ferrari in Montreal, but if you're in traffic, it doesn't matter. You can only go so fast as the car in front of you. So if the muscle can push 500 pounds, and the need is only 100 pounds, who gives a crap about the extra 400 pounds? So my bias is that, by all means, if you want to do it, but I don't really think it helps beyond a placebo effect. So what I'd like to do, tangentially, is that what would be cool is we're going to try to implement a 500 level class in kinesiology. You may not benefit from it, maybe you will, if we can get it implemented, but part of it would be kind of like an upper level grad and undergrad class where there would be pro-con debates about things exactly like that. Commercialized things related to exercise performance where students would debate each other. You would give the evidence of research evidence for, and somebody would give the research evidence against. And then try to convince the class in a debate style why these things, everybody should be running with these things and why nobody should. As an example, like why blood doping might work and why it doesn't. So you're critiquing the research, the methods, the physiology. So again, that course doesn't exist yet, but that's kind of the idea because I think they're really cool questions. Alright, so moving into VO2 max, which is relevant to what you're going to see in the lab. So VO2 max really can be analyzed in terms of the factors contributing to the oxygen transport chain. Okay, so we have a series of events of both what you'll see throughout the class is diffusive and convective oxygen flux or delivery. Okay, so movement of oxygen from the environment to the cell. So we have this pathway and the chain. The transfer of oxygen from the environment to the cell can only move as fast as the weakest link in the chain. Right? So, that's part of the problem with the oxygen transport cascade, is that if there's a weak link high up in the chain, so say at the level of your lungs where you have an impaired gas exchange efficiency or something due to emphysema or bronchitis, smoking-related disorders, whatever it is that now the limit to oxygen delivery to the cell and all the consequences that we just showed if you change oxygen levels actually now occurs in the level of the lung. So the muscle, everything like that could be fine, the blood vessels could be fine, but if you can't transfer oxygen from the lungs to the blood quickly enough, that's where the limitation occurs. Okay? So oxygen first needs to be inspired through the mouth and the nose, through the lungs, cross the blood-brain barrier. So we have convective oxygen delivery. So basically this is movement of oxygen through tubes with no aspect related to diffusion. It's still moving along pressure gradients, okay, and we create pressure gradients when we breathe, right? We breathe in, we create a negative pressure in our lungs relative to the atmosphere, and then so air sucks into the lungs along a pressure gradient, okay? So we get convective oxygen delivery. Between the lung and the blood, we have to diffuse oxygen from an area, from a high pressure area to a low pressure area. This is good, right? The blood returning from the exercising muscles, the mixed venous oxygen levels decline. We send oxygen to the muscle strips oxygen away, and what comes back to the blood is less oxygen. So we've created automatically a pressure gradient. The lungs, the pressure of oxygen in the blood is high, the pressure of oxygen in the mixed venous blood is low. We create a widening pressure gradient, oxygen diffuses, fluxes from the lung to the blood to support its delivery ultimately again into the heart for another form of convective. Bulk flow through cardiac output. Stroke volume, heart rate determine cardiac output. Cardiac output determines the bulk flow of oxygenated blood from the heart to the tissues. At the level of the tissues, there's local microvascular changes, vasodilating and vasoconstricting influences that dictate how much blood you get at the liver, the kidney, the brain, the muscle, the foot, the toe. Okay? So there's local vasodilator and vasoconstricting influences that will determine the convective oxygen delivery to the level of the cell. Now, the amount of oxygen in the cell will be determined again by diffusive oxygen flux. So how much oxygen is in the blood and how much oxygen in the cell. Again, at the onset of exercise, intracellular oxygen levels decline because oxygen starts being removed from the cell, right, in oxidative phosphorylation. That immediately creates an oxygen gradient for the diffusion of oxygen from the blood into the cell. So you'll see we have these patterns and physiological adaptations that automatically create pressure, energy gradients for the movement of oxygen from the atmosphere into the cell to be utilized through oxidative phosphorylation and to try to drive ATP in the most efficient manner. So, in the lab that you'll see this afternoon and tomorrow, you'll have individuals not doing a treadmill test, but a bicycle exercise test with a polar heart rate monitor and breath-by-breath measures of pulmonary gas exchange, measuring how much oxygen goes into the body, how much comes out, how much carbon dioxide goes in, how much comes out, your ventilation, your breathing pattern, all those various factors. And so ultimately, an individual that has a VO2 max or a maximum oxygen uptake, and you can debate whether or not somebody really has a VO2 max or a VO2 peak. I always use VO2 peak because most people become symptom limited before they actually hit a max. We'll talk about that in another slide. But that's typically within the normal age, sex, and height predicted range of 80 to 120% predicted. Suggests that there's no gross pathophysiological impairment in ventilation and pulmonary gas exchange, central and peripheral circulation, blood gas transport, metabolism, muscle function, the coordinated activity of all the different physiological support systems. In other words, it means that along this oxygen transport chain, you're pretty normal. Now, if the values fall down to 60, 50%, you got to start investigating, and you need to understand human physiology to begin to look at the different parts of the oxygen transport chain to figure out where the limitation is. If you're 130% predicted, well, that means that you've done something in terms of training to facilitate the movement through that oxygen transport chain at a higher rate to support a higher maximum VO2. So, during an incremental exercise test, so again, like you're going to do this afternoon and tomorrow, where you start from rest and at regular intervals you increase the intensity of exercise until you can't exercise anymore. Okay? It's not the way we exercise in real life, but it's the way we test somebody's maximum capacity. VO2 increases as a linear function of increasing power output, typically at 8 to 12 milliliters of oxygen per watt on a cyclic ergometer. So this would be a normal range. We use this range as an indication of muscle metabolic efficiency. And it gives indications of whether or not the muscle is incredibly deteriorated in terms of its function. There's a circulatory impairment, a muscle metabolic impairment, a myopathy, or something like that. So if you're using tons of oxygen for a given power output, that's not necessarily good. Okay, so you see this often in things like mitochondrial disorders or mitochondrial myopathies. Where the muscle is utilizing tons of oxygen to support a very low level of work. Okay? But we do have this normal range of about 8 to 12 mils of oxygen per watt. And this will increase to a point where oxygen uptake plateaus or fails to increase, typically by greater than 0.15 liters a minute, despite continued increases in power output. So the muscle, the oxygen uptake demands and the ATP demands continue to increase, but VO2 plateaus and fails to increase despite increasing work rate by an amount greater than 0.15 liters a minute. In other words, you've reached your VO2 max. You've reached the limit at which oxygen can be consumed through oxidative phosphorylation. So, this continued increase in power output and ATP demand is being supplied by what? Stored ATP, phosphocreatine degradation, and glycolysis. Because it's not coming from oxidative phosphorylation. Because we know that VO2 is proportional to the rate at which oxygen is consumed by the cell. So, it's common for tests to be termed submaximal if a plateau in VO2 is not observed, even though the subject does not consider the test to be submaximal. So it's a little bit deflating if somebody comes in and blasts out to 95% of their predicted heart rate, they're 10 on the Borg scale, you know, in terms of leg discomfort, ratings of perceived exertion, shortness of breath, but they didn't reach a plateau in their VO2. Are you really going to tell that person that they really didn't exercise to their max? It's actually very rare to get somebody to meet the criterion of a VO2 max. So I think it's more appropriate in research and clinically to describe somebody's maximum exercise capacity as their peak. Because most people will stop exercise before they've reached the physiological max when they've reached the symptom limited max. A lot of people don't tolerate the demands of exercise like 4 people this afternoon are going to be put under. So if you're not willing to tolerate the discomfort, you stop. Right? You don't want your hand to burn on an oven, it sucks. You don't leave it. It's like, oh, it's hot, you remove it. So if it's an unpleasant sensation, you stop, even before you've reached the physiological max. Your hand can burn, you're not going to die from a burned hand, but you remove it because it's unpleasant. Right? So, a plateau in VO2, in fact, actually occurs in less than 35% of healthy subjects making a maximum voluntary effort. So you give all you have, but you still don't reach a plateau. So again, I think the point is that a VO2 max is hard to get. You can get it in horses, because you can just keep whipping horses and stick them on a treadmill to run. So horses can achieve incredible VO2 maxes. They're freaks of nature. Their lungs are so underbuilt for the size of their muscles that they get like these pulmonary hemorrhaging and their lungs bleed and they bleed out. It's pretty crazy. So they give them diuretics to try to like decrease pulmonary edema. And anyway, some cool studies have been done in horses in Washington, and the whole concept of exercise-induced hypoxemia was actually identified by trying to understand why horses retain CO2 during exercise, and they found that actually they desaturate substantially. But so the vet exercise physiology translated into elite human physiology ultimately. But so horses can achieve peak VO2s, maximum VO2s, but humans less likely. So in most cases, as I mentioned, subjects cannot tolerate the discomfort associated with breathing and muscle fatigue to achieve a plateau in VO2. So in most cases, we're going to refer to things as peak VO2 more than VO2 max, even though the lab handout has VO2 max riddled all over it. Okay? So, as I mentioned before, the oxygen transport cascade is a serial system. So oxygen delivery cannot exceed the capacity of its weakest link. The higher up the chain, the worse it is. So a substantial increase in the function of any one step alone may not translate into a corresponding gain in exercise capacity. If somehow, through this power trainer, you increase the number of the surface area of the lungs and the respiratory musculature, and you can send more oxygen to the cell, but the cell hasn't adapted with increased mitochondria and enzymes. You can send more, but if it can't use any, you're limited by the number of mitochondrial enzymes, right? You're limited by the weakest link in the chain. So, increasing one step alone may not be enough to get a very substantial increase in overall peak VO2 or cardiorespiratory fitness. It might have to be a coordinated improvement in multiple aspects of the chain. And I'll show you a slide next about that. So, again, if the remaining steps of the pathway don't adapt, okay, so this is a unique example like the respiratory system in elite athletes, is that, as I mentioned, the respiratory system is incredibly overbuilt for exercise in all of us. Our muscle metabolic system is relatively underbuilt relative to our lungs. We have tons of surface area, a very efficient respiratory system, very efficient gas exchange system. The interesting thing is that if you were like an elite athlete, a rower, a Nordic skier, a cyclist, a runner, whatever it is, interestingly, the lungs do not adapt to exercise. They're weird organs. In a guinea pig, you can chop a lung off a guinea pig and stick it in hypoxia-like altitude and it'll grow a lung back. But exercise, for whatever reason, is not a stimulus for lung growth. So what happens is that you get a stronger heart, better ventricular function, more mitochondrial density, all these capillaries that begin to improve, right? Shift in fiber types, all of these things that make you more aerobic. But then, the lungs, a central component of the oxygen transport cascade, don't adapt. So elite runners, cyclists and things like that, ironically, they go to having a respiratory limitation to exercise. Whereas a respiratory limitation to exercise in all of us who have, probably reasonable, healthy VO2s, but not like world-class, Olympic level skier VO2s, the respiratory system is not a factor in limiting exercise. But when you become that fit, and everything else adapts, but the lungs don't, all of a sudden it becomes a limiting factor. So it's kind of a weird thing. It's like the lungs outrun the lungs, and the lungs outrun the heart and the muscles when you're untrained, but then the muscles and the heart kind of outrun the lungs when you are trained. So we'll look at some of the
At that point, it would be max unless it's the last control for
It could be, but again, if the limitation is not muscular strength, but is gas exchange and surface area, if the trainer doesn't increase surface area or gas exchange, then I mean having greater respiratory muscle strength. So they're good questions that I mean, I'm giving you a definitive answer, but it's not a definitive answer. That's what I have a tendency to do, but it is, I mean, I don't know. I think there's still more research to be done. And they do these meta-analyses or systematic reviews, and there's as many studies that are positive about performance-enhancing effect as there are negative. Again, what's placebo and what's real is kind of hard to figure out. So what we're looking at here is we're looking at a relationship between VO2 max in terms of a percentage of the actual value and one of these, basically the activity of any one of these determinants of the oxygen transport cascade. So we're looking here at alveolar ventilation, so the delivery of fresh gas to the lung through ventilation, lung diffusing capacity, muscle diffusing capacity, muscle blood flow, and the shape of the oxyhemoglobin dissociation curve, which will dictate basically the affinity of oxygen in hemoglobin and how much oxygen is unloaded, okay? And then subsequently delivered to the muscle cell for utilization. So really what we have is a theoretical representation of how individual changes in each of these major independent variables in the oxygen transport cascade affect VO2 max. So the figure shows by the red dot the normal values of each transport variable plotted against VO2. So you have a normal predicted VO2 and a perfectly normal functioning of any one of these parameters. So they're all operating effectively to give you a perfectly normal predicted VO2. So now if we move up and to the right and down and to the left, we look at what happens if you compromise the individual performance of any one of these independent variables, and if you improve the independent performance of any one of those variables in the oxygen transport cascade. And so strikingly, what do you notice about the slope of the curves in the bottom left quadrant versus the top right quadrant? Sorry? Right. So, for a given deterioration in any one of these physiological support systems, you get a pretty dramatic compromisation of peak VO2 or VO2 max, right? But the alternative is that training-induced improvements or whatever therapeutic-induced improvement in any one of these individual parameters results in a relatively modest improvement in VO2 max. So think about this in terms of your training adaptations. I've been training my ass off for 1.5 years and I hit a plateau. Yeah, because there's a plateauing effect. You have to have very dramatic changes in any one of these support systems to get a small measurable effect on VO2 max. But you go through a few weeks of bed rest, or you, heaven forbid, suffer a disease that compromises any one or combination of these physiological support systems, and you deteriorate in your maximum physiological function very, very quickly. So, you wonder why you can lose cardiorespiratory fitness much faster than you can gain it? It's because there's a relationship where the loss has a much greater effect on performance than the gains do. So, it's important to stay healthy. It's important not to smoke. It's important to eat well. Because small deteriorations in any one of these physiological support systems results in disproportionately large reductions in cardiorespiratory fitness. And cardiorespiratory fitness is a very robust independent predictor of long-term mortality and independence. So the lower your peak VO2, the more likely you are to die compared to when it's higher. And that's even in health. Individuals without chronic disease. Yeah.
If someone goes down on the left and sees their VO2 go down, when they start descending again, is it going to go up as quickly or as slow as on the right?
So yeah, well, it's a good point. Like if you, again, theoretically, if you started from here, you would get a very dramatic gain, but then once you kind of hit that, your predicted peak, so to speak, the gains will plateau. So to give you an example, last January 2017, I was 270 pounds and I couldn't walk up a flight of stairs. So I lost like 50 pounds and changed my body composition from 40% body fat, I'm down to like 12, 13 now. But within a very short period of time, I had dramatic gains. Like I lost like 35 pounds really, really quickly. And now I work out like 7 days a week and I eat like cottage cheese and chicken and stuff. I'm gaining like a pound of lean tissue every like 3 months, which is still pretty good gains, but I had a very dramatic change with a very, very shallow plateau. You just so yes, you can start low, like somebody with a very severe lung disease, and you can get very dramatic improvements, but once you've kind of hit this kind of physiologic limit, the gains after that are relatively modest. So the idea is to try to always stay at or above the factors contributing to your oxygen transport cascade to the extent possible. So let's consider some of the ideas on the limitations to somebody's peak cardiorespiratory fitness. So we got VO2 in terms of power output here, okay? So again, we're looking at the relationship between exercise intensity, so an indication of ATP demands, and VO2 on the y-axis from rest to maximum exercise. So we're going from A to C. So let's assume that somebody was able to exercise to a true VO2 max, right? There's a linear increase over most of the range to satisfy muscle metabolic demands in VO2, but at point B, VO2 fails to rise further despite progressive increases in exercise intensity,